Here. So the first speaker of the morning is Christoph Keitel, and he's going to be talking about quantum coherence at high energies.
Okay. 1, 2. Yeah, good morning. It's a pleasure for me to speak at this audience. Usually, most of the time, I'm speaking in the intense field community who are interested, building experiments on working theoretically with extremely strong laser fields. However, there are also situations which I think are of interest for the quantum coherence community, and I have tried to focus here on directions where this is of relevance, and particularly this is dealing with ions and nuclei, so interacting with, for example, free electron lasers. So that will be then involving high frequency physics, however, also involving coherent superpositions of nuclear states, ionic states, and so on. I hope you will not see that this is the same in green that you have with atoms. Our systems are different, so that needs particularly care. Treating the ions involving often QED, nuclei involving different interactions, also different problems. Nuclei have very narrow line widths. On the other hand, the free electron lasers are not as good as the lasers you're used to with, especially in the quantum optics community. They have broad line widths. So all these things need special care. However, we have also very different applications. Highly charged ions are important for astrophysics. Also nuclei are important for astrophysics. We can test fundamental theories, knowing this interaction, testing QED, for example. And also, applications like developing nuclear batteries and so on are things that are driving us in that direction. The key group leaders involved in at Heidelberg are Harman, Falfi, and Evers, and they have, of course, been very important here for those projects. Now, I'll start briefly introducing you in laser-ion interaction, and especially give you motivation why that is of interest, looking at those systems and sort of see how quantum coherence can be used in those scenarios. And then, of course, we'll go to these two directions I've been talking about. Ions, X-ray quantum optics will be looked at, for example, resonance fluorescence. And I'll give a couple applications that I think are quite useful involving quantum coherence. Building a frequency comp in the X-ray regime is one of them, and metrology applications, for example, to test quantum electrodynamics, and of course laboratory astrophysics are other applications employing ions, highly charged ions in particular. On the nuclear side, also nuclear quantum optics has been developing quite well, especially due to the advent of high frequency lasers, of free electron lasers, which are also quite intense, and in particular if you are able to accelerate those nuclei before the interaction, then of course you can even up boost the frequency, so you can really do quantum optics with those nuclei. And I will also show that sort of things like Rabi flopping, those things are feasible. Also stir up and so on with nuclei are of interest. And then of course I will focus on my sort of favorite application, isomer tricking for nuclear battery applications. You can imagine, of course, higher frequency means, of course, also that you can store much higher energies. That's why it is nice, of course, if you can transfer a nuclear state into some isomeric state where it can keep the energy, and then later you can trigger it. That's why this sort of isomer triggering is an important application for us. And then also things that I saw that could be interesting here, like phase-sensitive storage of X-rays using nuclear systems. We have two reviews on this recently. The first one, review of modern physics, is a bit broader. It includes the X-ray interaction plus extreme field interaction, the super strong laser fields. And the other thing is a bit smaller one, but this has a clear focus on X-ray quantum optics. Yes, yes. Is it? I'm not sure if it's still possible, but I try. Okay. Does it work? Okay, now we are. Thank you. Super. So, so let's start with ions. I want to sort of get you into those ions and those ions interacting with laser fields. Of course, mostly interesting physics is if sort of the two forces are comparable, right? So let's look at the lasers. On the laser side, we can do intensities up to 10 to the 22 watt per centimeter squared. This is not what we need here. And with Eli, in fact, you can even do better. And on the other hand, free electron lasers, high-frequency lasers, those are the ones of interest for this talk here, can go up to 10 to the 20 watt per centimeter squared. This is also a very high intensity. However, on the other hand, the forces you have in ions can be much higher. So whatever laser you come up with, there is an ion that is equally strong or much stronger. So if it's equally strong, that means you have usually tunneling recollision physics. That's the sort of things that you do lots in strong field physics. However, if the lasers are weaker, even though still use highly charged ions, then you have quantum optical situations. So resonant interactions are of importance. So we have two parameters usually in strong field physics, psi and chi, which tell us sort of the underlying regime you are. The psi is sort of more or less the velocity of an electron that it has in the laser as compared to the velocity of light. So this is, of course, the relativity parameter. And the other parameter, the chi, is the QED parameter. It tells us if we have to do a quantum electrodynamical treatment or not. In most of my talk, in fact, the lasers are weak enough that I don't have to be relativistic here in this talk, and also no QED is important from the side of the lasers. However, of course, if we have highly charged ions, then of course that part has to be treated using quantum electrodynamics. Now, I want to start with an application that you can see that there is some use in sort of looking at the interaction of ions with laser fields. And this comes from astrophysics, like here, this is embedded in an astrophysics institute. Also, me being in Heidelberg, also half our institute is also astrophysics. That's why this is definitely of interest for us. So in astrophysics, you look a lot at radiation coming from the interaction of photons, mostly high-frequency photons, with ions. And you can't do anything with it. You cannot change it because you have to take what you get. This is different, of course, in laboratory astrophysics, and different if you have lasers to try to simulate it. One of the scenarios, if you look at spectra from iron, this is a very typical situation you have in astrophysics. And the problem is they have usually plasmas, many ions, and in each ion there are lots of electrons. And the system is still highly charged, so even QED is part. So to model this, you have to do plasma physics, you have to do quantum electrodynamics, and you have to include the correlation. That's usually a hard task, and you have to do strong approximations. And so far, the theory has not been able to do a proper treatment of this to reproduce the experimental results. So one example is sort of these two lines from I-1917, and usually look at the ratio of the two to take off some of the effects, coming from densities and so on. And in all astrophysical scenarios, sort of the theoretical model and the experimental values were completely different, usually factors 3 to 4. So what colleagues from our institute have done, they have looked at the same ions interacting with the free electron lasers. And the nice thing is they can sort of change the system to take off some of the difficulties. For example, take away the plasma physics, so by taking small densities. And this was a group of Joachim Ulrich and Jose Crespo. They sort of took the EBIT to the LCLS in Stanford and looked at the spectra. We have done this theoretical calculation, And this was actually the first time our colleagues were happy that we didn't get the same. Usually, they sort of, we have a joint pair. So if we get the same, this time we get different results, and that was the joint nature. And the reason for this is that we saw that way that the treatment of the plasma physics was not the reason for the problem. What before the astrophysics always thought plasma physics is a more complicated part. That's why they have always these discrepancies. And in our situations in the EBIT, being at the LCS, the density was small. The same factor 3 deviation from theory and experiment. So that's very clear that the reason must be something else. More the treatment of the correlations and interaction with the photon fields. So that you can see there is a clear use of understanding interaction of photon fields with ions. However, I want to give you two other ideas, and this is more now theoretical, why you want to look at the interaction of ions with lasers. The one thing is here we took the example of bismuth lithium-like bismuth, so it has is a highly charged ion with a few electrons, and we looked at the interaction with free electron laser lights, and we looked at the resonance fluorescence spectrum. We know this from quantum optics. Usually, you get sort of a spectrum with some side length. This is what you get usually. So if you add another optical field, then you get quantum coherence coming into the game, at higher frequencies though. And sorry, actually this transition we do with an optical laser. And this way you change the resonance fluorescence, the same way you have it in atoms. And the nice thing here is, however, that this is known from atoms from the work by Narducci, Scully, and others, and they found these narrow lines. And now, if you have a system which includes sort of quantum electrodynamics, like in highly charged ions, then if you measure sort of the separation of these two lines, you get the Rabi frequency. And if the lines are very narrow, then you get a high precision in measuring the Rabi frequencies. And if you know the laser field, then you could use this to calculate the dipole matrix elements. And this way test QED to a high precision. So you see, by going to other systems, with similar ideas as you have in quantum optics, you get new applications. So this was a better, by an order of magnitude better test of QED than had before. And particularly, these matrix elements are important again for astrophysics, because those ions, often you you need to know the matrix element, and you don't have them usually. Yes.
Lines are not sidebands. Lower intensity lights are not sidebands.
These are sidebands. These are the Rabi sidebands. Yeah, Rabi sidebands. They're separated by the Rabi frequency. The lines are narrow, so you can easily measure the separation, and this way get the matrix elements. Usually, in atoms, it's not interesting because you have them. But in highly charged ions, this is interesting because they're difficult to calculate because they involve a lot of quantum electrodynamics. So the other... This was the 10 times better way of calculating these matrix elements for this scenario. I mean, for testing QED, actually, we had other ways of doing this together with Klaus Blaum and using ions and traps. That's better, actually, to do. But if you want to calculate these matrix elements involving QED, is what I mean, you can do this better than by other ways. So the other example I wanted to give you is building a frequency comb in the high frequency regime. A frequency comb usually involves a sequence of pulses, and you have a comb in the optical regime with sort of several spikes. They're quite narrow, and you have many of them. And there are lots of applications for this. You know this from the Nobel Prize of Ted Hensch. They're interesting for precision spectroscopy, test of fundamental physics, and so on. So there's a lot of interest in going to higher frequencies. A lot of people who sort of suggested that way you can even do even more stringent tests of fundamental physics. You can look at the variability of fundamental constants and so on. And there are also first works on this. There's Nature here by the Junier group, I think, which have done an XUV frequency combo ready, which is around 30 eV and 10 picowatt. So small intensities. This is based on high harmonic generation. The problem is here you use already lasers of the order of 10 to 14 watt per centimeter squared, and if you want to go to higher frequencies, then relativistic effects come in, and this is becoming then different, and then you cannot immediately apply this scenario because you have drift from the magnetic field of the laser field, and harmonic generation becomes much more complicated. That's why we have been looking at other ideas in a collaboration with Thomas Pfeiffer, and we are again using quantum coherences. The idea majorly is to use a three-level system, again ions, of course, because you want to write frequencies. You apply on one transition an optical frequency comp, and look at the generation on another transition in the X-ray regime. Of course, you need more to that to make it work. You need to create some coherence on these transitions first, but in principle that works. We know this all from four-way mixing and all so on, that these scenarios work. And we looked at this using several scenarios, and I'd just like to tell you the latest one, where we have sort of first imagined that it's a theoretical work. You apply here sort of an X-ray, like from the free electron laser, a pulse, and then you have an optical pulse here, and this way you create some coherent superposition on this some coherence between these two states. So similar like the old works on lasing without inversion and the high index of refraction from Mesoscale, in case you know that. And then in the second step you apply the frequency comp in the optical regime, and then together with this coherence, with this long living, because these two states have small decay rates, and the decay from this one doesn't affect this coherence, and then you can create a frequency comp on this transition. This is the main idea. And here are just the parameters. The system we have been looking at. We have been looking at helium-like beryllium ions. So the transition is 120 eV, and so the optical transition is at the range of 2 eV. So there are lasers on it. You need 10 to the 12 watt per centimeter squared for the X-ray pulse, and about 10 to the 10 watt per centimeter squared, and about for the laser, I think you need, doesn't say here, also about 10 to the 11 or 10 to the 12 watt per centimeter squared. And what you get out are peaks of the order 10 to the 10 watt per centimeter squared. So this is, at a higher frequency, at 120 eV as compared to 30 eV, which you had before. So that's the main idea. Now, in the second half of my talk, I want to go to nuclei. And with nuclei, we know that if you have nuclei sort of moving towards free electron lasers, then you can get resonances. And especially if you use nuclei which in the order of like 50 kV, 100 kV, with the MEV nuclei, this is harder. Yes? Yeah?
Just on the previous slide.
Yes.
So in this kind of resonance
This?
scheme,
Yeah?
three levels lambda scheme, there's sufficient bandwidth to support then a cone in step 3?
Do you mean the bandwidth on which transition?
Yeah, where you show X out, right? I mean, that train of pulses is that I assume that's time that you're showing.
The green one.
In
Oh,
the
yes.
frequency domain, you get
Time, yes, the same figure here is time, yes, nanoseconds, yeah. I'm sorry, it was cut off in the other thing, yeah. It's on top here, this is time. Yeah? So you see it here blown up. So in principle, as you know, whenever this optical spikes come, then basically you create this coherence 1, 2. You know, this is here. You create this coherence. Whenever this comes, each spike comes, and you create this coherence, and the other one sort of goes down for some time. This is a long time coherence because there's decay rates of these levels, you know, are very small. So you have to we picked a system where decay is small. So that's the idea. Okay. Now with nuclei, of course, everything gets a bit harder because the frequencies become even bigger. So we look at the nuclei sort of moving towards the free electron laser with moderate gammas, and that way you can get resonances. Usually these lasers you have around 20 keV or like some like 12.5. So you take a gamma of 4, then you can sort of reach, for example, for radium, the resonance on this transition, and that way you can get things like Rabi flopping in nuclei. Other ideas are sort of doing steer up with nuclei. You apply sort of laser on one transition and afterwards on the other transition. That way you can transfer population from one state to the other one. This sort of, the main idea behind this is sort of to create nuclear batteries to sort of move the population. This is demanding. You need reasonably high gammas, one has to say, and also the free electron lasers for that, they need to be sort of more the future ones, which have higher coherence. The seeded XFEL are necessary for that one. So I want to see if these sort of are mostly basic nuclear physics. I want to do a bit more advanced coherence interference effects, and I want to go a step back of how we related, how we sort of did this using atoms first. So here the idea was sort of to modify Fano resonances in a joint work together with Thomas Pfeiffer. So usually, of course, if you sort of have an excitation of the state, you get an absorption spectrum. But if you have sort of Auger decay, so then you have sort of two passes to the same state in the continuum, and then you can get sort of Fano type interferences. And the question was more or less, can we also, using quantum coherence and interference, can we sort of switch here with this? And I first showed you this with atoms, and the second step I show you this with nuclei. And this is a joint work together with Thomas Pfeiffer in his lab. And basically, so we have here an atomic sample, and this first experiment was with helium. If you apply sort of a probe field, then you usually get spectra, which are like in this case, for example, Fano type. And then the idea is basically you apply a second control pulse and you give a kick in time. And by kicking it in time, you sort of have this phase shift here, and that way the new response can be switched from Fano to Lorentz types. You can also affect the absorption spectrum, from gain to loss and so on. This is with atoms, and I want to show you like how Jörg Evers, this is in my division, has done it with nuclei, and he uses here Mössbauer iron nuclei, which transition here on the range of 14 keV. This is a frequency that can be achieved with free electron lasers. And here he gets the sort of interference by having sort of this substrate. Here you have an iron layer, and sort of you can have immediate reflection, or you can have this interaction with the iron, and then these two sort of beams can interact. And sort of the experiment that he has done together with Thomas Pfeiffer is basically, then after the theory, he has done it also experimentally, and he has also seen that by sort of shifting the incident angle, that this way by changing the angle you can sort of shift, change the phase between these two pathways. And again, he can shift in nuclei now from a Lorentz profile with to some dispersion-like Fano profile. So you can see, so you can do quite similar things with nuclei than with atoms already. The last thing I was asked to quickly show also here, also sort of spontaneously generated coherences can be done with nuclei, again with irons. Sort of you remember this, that you have two states which have sort of the same dipole moments here. You can sort of get sort of interference effects here by coupling via the vacuum. For this to work, you have to make sure that in the sort of in a cavity environment you only allow certain polarizations. And also here he has seen, together with the student Haig, that you can get also, like predicted in theory, interference effects, EIT-like interference effects in the spectra. Now I want to move to also nuclei and two of my favorite topics again.
Yeah? EIT-like? Is it EIT or is it not?
Well, these interference-like. You know, this is sort of this is spontaneously generated. I mean, it's via the coupling via the vacuum. So, like in EIT, of course, you have not the coupling via the vacuum, right? This is sort of work. It's not the same, but it's quantum interference. That's why I sort of maybe should not have said EIT-like, but it's via this extra pathways via the vacuum. You know, like.
Phono. It's like more like a phono kind of interference. Anyway.
Yeah. It's two pathway interference. You know, you have the same two passes going to the same final state, and that you have in EIT, that you have also in these spontaneously generated coherences, and also in the phenotype. In that sense, they're all related.
Both those upper states decay, right? Both of the two upper states decay.
Yeah.
So they interfere.
Yes, they interfere.
Or
Yeah, via this coupling via the vacuum sort of. You know, so you have to the same. You know, can go up and down, or you can go this way to the same state. But for that, you have to make sure that damn it, where is it now? You have to make sure that sort of you only allow sort of the same vacuum mode, so that these has to be the same vacuum modes to work. Now, the next thing is nucleosome triggering. This is again a nuclear system, molybdenum in this case, and we want to be able to move nuclear population to some particular state, keep it there, and then at demand later sort of release it with something we can control. That's useful, obviously, for nuclear batteries, for example. That's why this sort of nuclear isomer triggering is an important idea. This is sort of long in the community. You know, the first works were this by Walker and others who sort of discussed that this would be a wonderful thing. However, it has always been difficult to implement, obviously, because the nuclei parameters are different than in atoms. The line widths are very narrow. That's why it's hard to handle. And also in the old days, of course, there were no lasers that had the right frequencies to deal with this. Now, however, if you look at a system like molybdenum, then you see, you know, there's here an optical transition. Wait a moment, not optical. This is a transition which is feasible with free electron lasers, 5 kV. This is accessible with the free electron laser in Hamburg, for example. And then if you sort of, this has a long lifetime, so here you can store the energy. And if you sort of trigger it up, then, you know, it goes down like crazy and you know, can gain MeV energies. This is the usual thing about it. Now, what have we done? We looked at the interaction of sort of a system, a solid state, including those embedded with these molybdenum ions, nuclei, and interacting with a free electron laser. And there are two different ways this triggering can happen. The first way, this was a direct way which has always been known and which has always been small. And that was a problem so far. You know, so we have the problem, we have this very small line width of this transition. And the free electron lasers have a broad line width. So the effective coupling is very small. And that's why this triggering mechanism is a problem. However, so we looked now at a different mechanism. This is the one that the free electron lasers sort of induces some ionization. So electrons come up and they build a plasma. And those electrons can sort of be recaptured into some of these free shells and with the right energy can excite the nucleus. You know, this is nuclear excitation by electron capture. This is sort of a mechanism well known in astrophysics and in nuclear physics. And it's basically, you know, it's sort of a combined secondary process. And you would usually think secondary processes, they are small. You can forget about it. But still, we have done the calculation. And the reason why we were hopeful is that the time scales are different. And also the width of the distribution of the electrons are much broader. You know, there are lots of collisions and and you know, they're more governed by the plasma dynamics, not by the pulse of the free electron lasers. And we looked at both sort of rates, you know, for this way and the other one, and you know, there's a competition, and we sort of compared first the direct process for this transition, and we got rates of 10 to the minus 15, so tiny rates using the direct process with better free electron lasers. So this is with the LCLS. With the ones that are with the seeded free electron lasers, the situation will be better. But the present one, the rates are very small. And then we looked at this via the secondary process, and we've seen the numbers are at about 6 orders of magnitude bigger. And that's why we are now sort of more hopeful that this triggering nuclei can happen employing this other mechanism, which you can see is in particularly high if you can induce high plasma temperature. So if you have strong lasers. Yes, please, Sana.
Can you go back?
Yeah, sure. Yes?
So is that a Auger process or what?
No, this process here, this one is secondary. This is a capture process. So the electrons, you know, if you have apply a free electron laser, you know, this has high frequency, so it can take out some electrons, also deeper electrons, you know, not only the outer electrons, so they near the core electrons. And then the electrons fly around, and then of course those electrons can also be captured back. And when they are captured back, they release energy. And if these photons, usually these photons can be emitted, or you can have sort of an internal process. These photons immediately go to the nucleus and excite the nucleus. And then you have the excitation. It's the opposite of internal conversion, yeah. This internal conversion is, yeah, you're right. This is maybe more common, but this NEC is, among astrophysicists and nuclear physicists, is a more common process. And these are the sort of the competition. And what we have seen here is sort of that this, in fact, is a leading. The second order is a leading process and makes the whole thing much more likely, such that triggering can happen. Here we looked at sort of in which states they trigger and so on, but this I think I should spare you with. This is work with Adriana Palfi, group leader also in my division. Last project also with Adriana Palfi is also an idea of, I think this is also in this community important, be able to store photons and, you know, keep them a while, then release them again. This I don't do with optical photons, but with high frequency photons. Still, I think this is interesting because, you know, we heard also yesterday, you know, trying to get smaller devices is nice, and of course, if you have, you know, systems with, you know, smaller wavelength, that's always attractive to even for quantum information. So that's why we sort of looked at scenarios where X-ray photons can be stored, can be manipulated, and released at demand. And again, the working horse in nuclear physics is the Mössbauer ion transition. It's 14 keV. So that's the one, you know, most of the free electron lasers, in fact, were built to sort of have this transition available. And, you know, here you see that sort of you have, you know, if you have a magnetic field, then you can have splitting and so on. And these are, you know, these nuclei are embedded into some solid material. And then usually you have a probe field. And, you know, that can, you know, have absorption. Of course, you know, there's possibilities for coupling, interference, and so on. And then the magnetic field is there sort of to control the whole thing, to change the splitting and sort of to make different level constellation feasible, like in the experiments from Jörg Evers you have seen before. And typically you get spectra like this, you know, here like these quantum beats and so on, you know, look a bit complicated. But now the question is what we asked, what happens if you switch off the magnetic field for a short time? And that's what we've done here. Now, this is the first figure is like the one I've shown you before. No, you know, the magnetic field is on all the time. The magnetic field is that one here. But now, if you switch off the magnetic field for some time, then we see that you know, these spectra stop for a time, and then sort of it continues as if nothing has happened. You know, a small decay because of spontaneous emission, which is not very big, but essentially you have sort of stored the photon, the X-ray photon, for a while and then released it again. If you're not happy with this, you want to change the photon, you can also do this. For example, here you keep the magnetic field, and then you, after, here, if you just keep it off and then on the same direction, then it was like before. But if you sort of turn the magnetic field, then you have a phase shift of pi. So you can either have sort of a storing, phase sensitive storing, or you can even change the phase at least to some degree. And with this, I think my time is up, and I want to sort of conclude. And I hope I've given you a little introduction into, I think, interesting things you can do employing high-frequency lasers with the corresponding systems, which are ions, highly charged ions, and nuclei. So it's in a sense, it's a similar quantum optics as you're used to it. However, of course, with higher frequencies. We have our own problems, including QED, also that the line widths are not as we like. The matrix dimensions, of course, are very different, but also our applications are very different. And I think many directions are also interesting. For example, you can do high frequency comms. You can do laboratory astrophysics. You can also sort of do nuclear transfer of nuclear populations and do isomer triggering, for example. Create nuclear superpositions. And store photons, phase sensitive, and even change them at will if you want. So similar things that you're used to it. Thank you for your attention.
So we have time for a few questions.
Hey, Christoph, I probably missed it, but you have this lambda system where you use a frequency comb, if I understood it right, some spectral range visible,
yeah.
And then you convert it to an XUV X-ray frequency comb with a loss of a factor of 100 intensity. Right? Yeah. And so I was wondering, how far can you push this? Could you find a lambda system where you pump in the optical, say with the titanium sapphire,
and that way gain the energy
very efficiently make an X-ray frequency comb?
No, I think you cannot upconvert the frequency. I mean, of course, you want to hope to gain some energy by the low frequency field. I mean, all the low frequency can do, it can sort of it can shape the spectrum. You have the sort of usually the normal free electron laser spectrum, right? This is a no comb, and then of course the optical can just shape the spectrum, but you cannot put more energy into it. This I think doesn't work because it's got a completely different energy range.
Then I was probably missing something. So how do you get? You have to get to I think what you call level 2 or 3 first.
Yeah.
Before you can fall down to level 1 and get the induced train.
I mean, basically, the first step is just to create the coherence here, because without the coherence, nothing can happen. Because you need, in order to affect this coherence, you need to get this indirect coupling via this way, So here, this field sort of couples with the optical field, and then also this extra coherence you need. That only that way you can affect the coherence here, and that way, of course, via this polarization or this transition, of course, then you can create the right, the right outcome.
So before all of this happens, you first have to pump up from 1 to...
Yeah, somehow you have to pump in some energy. And this, of course, can only work if you have a free electron laser. The free electron laser puts in the energy. And the optical comb sort of does a shaping. Gets the structure into it.
But still, I mean, you get the energy from the free electron laser.
Yes.
And then you just drive 2 to 3 and kind of synchronize then the output pathway with that.
Yes.
So consequently, you still can have a really good return.
You could do what?
I could imagine you can still get a very good return because you have plenty of energy from the pump process. It's just not synchronized.
Yeah, I mean, this loss of 2 orders, I see this actually I haven't been to award about before, but I think maybe we can improve that. So it's we haven't worked on that, to be honest. But that's a good point. Yeah.
Question?
Actually, can you think about this project and again the storing of light because it have the same 2 steps. You create the coherence with 1 or 2 pulses, and then you read it out with the optical pulse, and that generates the readout on the other field. I think intensities are a little backwards, but Can it be thought like this process and do some optimization this way?
I didn't get this much very well. So do you want to optimize
so
what you get?
Can you think about this process as the storage?
Oh no, not this. Talk
This
about,
one.
oh.
Yeah, this one. Because you create
A
coherence
storage?
between 1 and 3
Yes.
using the pulses,
Yes.
and then you trigger your readout using the optical cone.
Yeah, you can see it also that way. So in a sense, yeah. Okay. Yeah. As triggering process. In sense,
But then
yeah.
can you somehow manipulate how your pulses, maybe optical pulse, looks like at the first stage to increase the efficiency of the comp readout? Because that will affect
In a
the
sense,
coherence as well.
I mean, in a sense, you just want to maximize this coherence, and I think that's so. Basically, we need resonance in here. I think the shape is probably they are not so important, but I mean, I don't see what to optimize there as long as we have maximum coherence. Of course, we have to be fast afterwards because here this guy is decaying, and but I think let's see.
Much another question, and then we have to move
Okay.
on.
Yes?
What was the time delay between your pulses and the frequency? I mean, the train of the pulses.
So
This
it's
eats out.
the lifetime of the coherence, right?
What do you think between these
What
two
is the
steps?
time delay between sub-pulses and your frequency comp?
Well, as short as possible, I think. I mean, this is a principle. You create the coherence, and then afterwards the pulse should come. I mean, of
But
course.
you create a coherence that will decay within the life.
Well, the problem, yeah, of course. I mean, but the good thing is it will decay only with decay of this state, because this coherence between this one is, and that's why we've done it this way actually. That's why we had two other papers before. We had this always not so attractive, because we involve decay rate. If you involve this decay rate, then the peaks become much broader, and also the whole spectrum won't be as broad. So you definitely need to avoid this decay. And the nice thing is here, this is a state which decays very slowly. So that's the way we picked the system. I think this helium-like beryllium ions, just this state has a small decay rate. Of course, this is important. We have to be fast as compared to this decay rate, because we don't want to have lost the coherence by that time. That's a crucial point. But this time is not short. Yeah.
Well, let's thank the speaker one more time.